by stating, or by proving the theorem of the primitive element. This said that if L over K is a finite separable extension, then it's a simple algebraic extension. For some element A in L. Okay, so we will continue later. I mean, this will be one of the kind of cornerstones that we use to do our algebra theory. We will continue later with that. First, I make a short interlude on finite fields. We want to give a classification of finite fields up to isomorphism. Because it's quite simple at this stage. It's a nice no. We want to classify finite fields up to isomorphism. So what finite fields do we know? Until now, we know the fields FP, which is just Z, say Z modulo PZ or ZP with addition and multiplication. So, and we want to claim that there are more such things for P a prime number. And we want to show so if F is a finite field, then the number of elements of F is a prime power Q equal to P to the N for some prime P. And
this is just corollary of Silo theorem. Silo theorem. This is corollary of Silo.
I don't think so, no. Why should that be a corollary of Silo's theorem? Because you know, we are wanting to
Gottsche theorem also implies this fact, Gottsche theorem. If there is another factor, another prime number, such that divides order of phi, then we consider additive group of this field.
Yeah. No. I mean, that's okay. So this thing is quite easy that this is the case. I will give another proof, but it's very simple. But so the non-trivial thing is that up to isomorphism, there is only one field of this order. And up to isomorphism, for every prime power Q equal P to the N, there exists a unique field of order P to the N. Now, so I'm not quite sure, but it is possible that one can prove that only such finite fields only exist for prime powers. At any rate, it's yeah, that might be the case, but I give a different proof. So this is just the following remark. Let F be a finite field. So if it is finite, it has to have a finite characteristic, and we know the characteristic has to be a prime number of characteristic prime. Then F contains the following subset. This is the set of all n times 1 with n in Z in the field. So all the multiples of 1. And this is just, we know that if I take p times 1, this gives 0, and every time before it gives something different. We can easily see from this that this is isomorphic to Fp. And so if it is a finite field of characteristic P, then, so that means, so then F contains, is not equal, F contains it contains Fp as a subfield, so it's a finite extension of that. So thus F is a finite extension of this subset, which I can maybe just write as Fp. And so, and thus the ordered number of elements equal to p to the n, where n is equal to the degree of F over Fp. Because it's a vector space of dimension n over Fp, and so it has p to the n elements. So I think most likely one can also do it in easy ways from the Zülow theorems, but this is how I want to see it here. So now we want to have the non-trivial effect is to see that such fields actually exist and that they all who have the same number of elements have to be isomorphic. I mean, it's not difficult, but anyway. So first, the following lemma. So I will write always Q equal to P to the N, where P is a prime, that we don't have to repeat this all the time. So first, the lemma. F be a field of characteristic P. Then I can look at the following polynomial. I take x to the q minus x, where q is p to the n for some prime number, has q simple roots in its splitting field over F. So if I view this as a polynomial in Fx, it has in its splitting field. And that's almost trivial because we know that a multiple root can only occur if we have zeros of both the polynomial and its derivative. But let's look at this. So let A be a multiple root. Then A is a 0 of x to the q minus x and of its derivative, and x to the q minus x prime, which is, so this is q x to the q minus 1 minus 1, and q is equal to 0. So there is no such 0, and so there is no multiple root. And so all the roots are simple. And so now we want to show there exists a field with q elements. for every q equal to p to the n. For p a prime number. So for this, proof, we look at the splitting field of the self-same polynomial over Fp. So let L splitting field of x to the q minus x over Fp. And now, for the moment, actually, we'll later show that this is a field with q elements, but for the moment, we don't know this. Now we just look at all the zeros of this polynomial in this field. So let F be the set of all A in L such that A to the q minus A is equal to 0. So that means A to q is equal to A. So this is the set of zeros of x to the q minus x. So clearly, F has q elements. We, after all, had just seen in this lemma. And now we want to see that F is a field. So we just can, obviously, we have 0 and 1 is in F. And if A and B are elements in F, then we can, for instance, take, if I take A times B to the q, this is A to the q, B to the q, but A to the q is equal to A, and B to the q is equal to, this is equal to AB. That means AB is in F. Same if I take the inverses. So 1 over A to the q is equal to 1 over A to the q is equal to 1 over A. That means 1 over A is in F. And also if we take the sum of two elements, or the difference, A plus minus B to the q. Now, this normally would compute by the binomial theorem, binomial formulas of all these binomial coefficients. But you know that all the binomial coefficients except for q choose q and q choose 0 will be divisible by q. So therefore will be 0. So this is just equal to A to the q plus minus B. So it's equal to A plus minus B. Okay, and so that means A plus minus B. So F is a field. So we have found some field with q equal to F to P to the n elements. And now we want to more precisely characterize what these fields are. The claim is that in some sense F is actually equal to L. So that a finite field with P to the n elements has to be the splitting field of this polynomial, x to the q minus x. Proposition. So let F be a field with q equal P to the n elements. Then F is a splitting field of x to the q minus x over Fp. let's see why is that the case. First, we have to see that every element in F, so we will show instead that every element in F satisfies this equation. So first, every element A in F satisfies A to the Q minus A is equal to 0. Why is that? So if A is equal to 0, this is clear. And otherwise, we are in F in the multiplicative group. So F star is a group of order Q minus 1. So we know that any element in this group, if we take it to the power Q minus 1, we get 1. So thus A. So thus if A in F star, then A to the Q minus 1 is equal to 1, and we can multiply this by A, and so A to the Q. So this is the first part. So we see that every element in F satisfies this equation, like we had here. And conversely, and to see that it's actually the splitting field, want to see, so as x to the Q minus x has degree Q, and we also know it has no multiple roots. Because of the previous lemma, we get it has Q in F. So Q distinct roots in F. So thus, x to the Q minus x splits over F into linear factors. So this polynomial splits. On the other hand, we know that F consists only of zeros of this thing. So there can be no intermediate field between F and FQ where it would split. So as F consists only of zeros of x to the Q minus x, it is the splitting field. It of x to the Q minus x over FQ. FP. Okay. Now, so we know that splitting field is well defined up to isomorphism. So therefore, it means there is up to isomorphism only one field with Q equal P to the n elements. So if I put this all together, I get what I said in the beginning. So a finite field with m elements exists if and only if m is a prime power Q equal to P to n, and for a prime power p to the n, there exists up to isomorphism unique field with p to the n elements, namely the splitting field of this polynomial x to the, say now, p to the n minus x over fp. Okay, so this was just a simple thing, but these finite fields do play a role in some things. Also in algebraic geometry, they are quite important. So it's nice that they can be described in such a simple way. Okay, so this was some kind of interlude. Now we want to go back to the mainstream of our argument. And so we want to talk, to continue our way towards Galois theory. And so I now formally introduce the Galois groups, and we study some of their properties. Then the next time we will show the fundamental theorem of Galois theory, which relates subgroups of the Galois group to intermediate fields of the field extension. So let me introduce Galois groups. After Évariste Galois, who the inventor of Galois theory. So we study field extensions L over K via the group Galois group of L over K of K automorphisms of L. So this is therefore the definition. If I have a field extension the Galois group is just the group of K automorphisms. So the Galois group of L over K, so denoted Galois group of L over K, is the set, or is the group of K automorphisms of L. So of automorphisms of the bigger field L, which are the identity on K. Clearly, this is a group under composition. So one example that everybody is familiar with from the complex analysis, we have the complex conjugation. We denoted tau from the complex numbers to itself, which sends a complex number A plus BI to A minus BI. This is an element, this is an automorphism of the complex numbers. It's compatible with multiplication and addition and so on, and is an element of the Galois group of the complex numbers over the real numbers. No, it's the identity on real numbers. So we want to try to get some understanding of these groups. So let's first try to understand them for simple algebraic extensions. Study them. For simple algebraic extensions. Okay. Okay, recall that for set M, we have S of M is just the set of all bijections, sigma from M to M bijections. And this is a group under composition, and it's isomorphic to the symmetric group M in as many letters as there are elements in M, if M is finite. Okay. Now, so as I said, I want to look in the case of simple algebra extensions. That's basically what I'm saying is more a reformulation of what we have already proven, but it's important tool to know this. So, theorem that Ka over K is simple algebraic extension. So say of degree n. So the degree of the Finite extension is n, which is also the same as saying that the degree of the minimal polynomial of A is n. So let f be the minimal polynomial. Of A over K. Then we look at the roots of this minimal polynomial. Or B in Ka. So all the zeros of the minimal polynomial in Ka. So zeros of f in Ka. Then the statement is the Algebra group of Ka over K acts simply transitively on R. So in particular, if it acts simply transitively on R, we know that the number of elements in the Algebra group is as many as elements in R. And as they are the zeros of this polynomial of degree n, this number of elements is smaller or equal to R. So we get, so thus the Algebra group of Ka over K. Order, well, if you want, isomorphic to a subgroup of SR of order R. N. So as the Galois group acts, it acts by permuting them, so it's isomorphic to a subgroup of this, and the order is at most R. So let's see. As I said, so we use a trick which maybe as we will use it many times, I maybe make it a remark. You don't have to always. So that L over K be a field extension. So F, a polynomial with coefficients X, A in L is 0, so A an element in L. Then if I take, so if you write F equal to sum I x to the I, then what happens if we apply phi to F? Then, so if I take of F of A equal to, so I can pull, the coefficients Bi are in K, so they are invariant under the Galois action, under the action of phi. So this is sum I Bi of A to the I, which is equal to F of phi of A. In particular, if A is 0 of F, then phi of A. Because obviously in a field, isomorphism has to send 0 to 0. Okay, so this is something that we'll use 3 or 4 times in this course. So now let's look at this. So now we come to our proof. So this is self-evident, but now come a proof of the theorem. So what do we want to prove? So let B be an R. That means F. So if element in the Galois group of Ka over K, then by the above, we have that F of phi of B is equal to 0. That means phi of B is also an element in R. So thus, if we take phi, our element in the Galois group, and restrict it to R, this maps R into itself. Obviously, phi is injective because it's an isomorphism of fields, so it is injective. In particular, its restriction to R is injective. So therefore, it is a bijection of R to itself. We have that an element in S of R. Permutation. And more, so phi restricted to R is an element in S of R. So we can write this more mathematically. So we get a map, get a homomorphism. So restriction to R from the Galois group of Ka over K to S of R takes element in the Galois group, so an isomorphism of Ka to itself, which is the identity on K, and restricts it to R. Phi extend to phi R. This is clearly a homomorphism. The composition here, the product here is the composition, the product is also the composition here, so therefore it is clearly a homomorphism. Now, we know the story with the extension of field homomorphisms to simple algebraic extensions. So, you've seen for any two roots, say P1 of F, there exists a unique element in the Galois group okay, which sends P1 to P2. No, because the statement was that for simple algebraic extensions, for any two roots of the minimal polynomial of the element giving us the extension, there exists a unique extension of the identity on K, which sends 1, 0 to another. And so this is just this statement. And so this precisely means that the Galois group acts simply transitively. On R. And if it acts simply transitively, it also means that, so for any, it also means that this map here, from here to here, is injective. So thus, restriction to R from the Galois group of over K, so S of R is injective. Because it's actually, it's simply transitively, so if I know what it does to one root, I know which element it is, so the map is injective. And so, therefore, thus, the Galois group Ka over K is isomorphic to a subgroup of S of R, image. And as it acts simply transitively on R, it has as many elements as R. And number of elements in the Algebra group of Ka over K equal to the number of elements in R, which we know that it's smaller equal to n, because we're looking at the zeros of f, a polynomial of degree n, in Ka, and it might, if it splits completely, it can at most have n different zeros, but it might have less. Okay, so this is this statement. So not particularly difficult, but it's useful to do. So as an to have, one can use it freely. So as an example, just look at two examples of Algebra groups. So for instance, I mean, see what kind of things can happen. So we can look at the Algebra group of Q square root of 2 over Q. So this consists just of two elements. The degree of the field extension is 2. So the number of elements in the Algebra group can be at most 2. And in fact, there are 2. It consists of the identity and the map which sends square root of 2 to minus square root of 2. So A plus square root of 2B, so where A and B are real numbers, sent to are rational numbers, to A minus square root of. Okay, so this is one example. So in this case, we see that this has this group has, I mean, the polynomial, the minimal polynomial x squared minus 2 has 2 roots in this field, square root of 2 and minus square root of 2. Therefore, we know that the number of the elements in the Algebra group are indeed 2, and we have precisely one. We have 2 elements. One sends square root of 2 to itself. The other one sends square root of 2 to minus square root of 2, and then it does that. So this follows from the statement. Anyway, it's also obvious, but it also follows from the statement. And another case where we can see that things can also be different is, for instance, we can look at the Algebra group of Q, the third root of 2 over Q. In this case, we know that this polynomial has, so if I take the minimal polynomial, x squared, x to the third minus 2 has third root of 2 as only 0 in Q third root of 2. So that means, as the action of the Algebra group is simply transitively, it means there can be only one element in the Algebra group, and obviously the identity is always there. So thus, the Algebra group of Q third root of 2 over Q is equal to the identity. The identity of Q third root of 2. Okay, so these are these examples. Okay, so this was the case of the simple algebra extensions. We will mostly be, so what one is really interested is the Algebra group of a polynomial. And by this one means the Algebra group of a splitting field of the polynomial over the ground field. And one will want to kind of try to understand the zeros and so on of the polynomial in terms of this Algebra group. So let me introduce that. But I'm actually, yeah, I was a bit ahead of myself. I mean, first I have to talk about, I want to say what is a Galois extension? So we are interested, so in Galois theory, one mostly studies for Galois extensions and their intermediate fields, where a Galois extension is an extension which is both separated and normal. And so definition, field extension L over K is called a Galois extension, finite field extension. Called a Galois extension if it is separated, separable and normal. Separated or separable? Separable. If it is separable and normal. So now let's just translate what we have here to that case. We have the following corollary. That L over K is a Galois extension. Then of degree n. Then the Galois group of L over K is isomorphic to a subgroup of symmetric group in n letters, the same n, which acts transitively on the set 1n, and in particular we have that the number of elements in the Galois group, the order of the group, Galois group, is equal to n, so the degree of the field extension. I mean, very often this is somehow the main thing one uses, that for a Galois extension, the degree of the field extension is equal to the number of elements in the Galois group. So why should this be a corollary? We don't seem to be talking about anything related. I mean, here we have this Galois extension, there we have a simple algebraic extension, but obviously we can here use the theorem of the primitive element, so L over K will then be a simple algebraic extension, and then we just apply the theorem. So proof. So by the theorem of the primitive element, that's why we have assumed that the extension has to be Galois, so in particular separable. You can write L is equal to Ka for some element. A in L, the primitive element. So as L over K is separable and normal, the minimal polynomial Fa of A has n distinct roots. In L. Maybe I should say a few words why this is. So as it's separable, we know that the roots are all distinct. So all the roots in the splitting field are distinct, so all the roots are distinct. So as it's a normal extension, we have that every irreducible polynomial with a root in L already splits in L. So in particular, the minimal polynomial of f is such a polynomial, so it already splits into linear factors, and all these linear factors are distinct. So we have n distinct roots. And then by the previous result, we have that the Algebra group acts simply transitively on them. Simply transitively on these roots. And that shows it. Okay, as I said, this is maybe not quite as important, but in particular, so one quite often just uses this fact that the number of elements in the Algebra group for a Algebra extension is equal to the degree of the field extension. So, I mean, for instance, we can see in this example that this is not a Algebra extension, because the degree of the field extension is 3, but the Algebra group has only one element. So we want to study a little bit more what the Algebra group does to elements. And one thing which is useful in proofs, which we also use in a moment in a proof, is we ask ourselves, if we have two elements, we have a field extension, we have two elements in the bigger field, when will there be an element in the Algebra group which sends one element to the other? The answer is if they have the same minimal polynomial over the ground field. So proposition. So let L over K be a Algebra extension. And we take two elements in the bigger field. There exists an element in the Algebra group of L over K, which sends A to B, if and only if A and B have the same minimal polynomial over K. Over K. Okay, so let's see. Why is that the case? So in one direction, we basically use again the extension to simple algebraic extensions, the extension of field homomorphisms. So assume that A and B have the same minimal polynomial. Okay. then by the extension of field isomorphisms, so then there exists a unique isomorphism say psi from A of A of B, which sends A to B. This was the extension of field isomorphisms to simple algebraic extensions. Now, we can further extend it to, we have the further statement that we can extend to splitting fields. So L is a, over K is a Galois extension, so L is a splitting field. So L is a splitting field some polynomial of some polynomial f in kx over k. But if it's the splitting field of f over k, it's also a splitting field over any intermediate field. So thus also over and over kb. So f is also the splitting field of f over ka and the splitting field of f over kb. And then we can therefore use the extension of field isomorphisms to splitting fields, which says that there is always an extension to the corresponding splitting field, which is L. By extension to splitting fields, there exists an extension psi Algebra group of L over K with P of A so to phi of A is equal to psi of A. So the extension to splitting fields says there is an automorphism of L which extends our psi. And then obviously, as this is as already psi is a k automorphisms, also phi is a k automorphism, so it lies in the Algebra group. And as psi sends A to B, then also phi does. Okay, and that's one direction. And the other direction is, so to do the converse, so we have to see that if I can send A to B via an element in the Algebra group, then they have the same minimal polynomial. So let A and B be elements in L. Of A some Algebra group. So now we take the minimal polynomial of both of them, and then we have to show that they are actually equal. So let f minimal polynomial of A over K and G of B over K. So we use again the same thing. We apply phi to this thing. So we know then 0 is equal to f of a. And so also, therefore, phi of f of a, which is f of phi of a, f of b. So we see f also vanishes at b. So f of b is equal to 0. So thus, as g is the minimal polynomial, we have that g divides f. Obviously, we can exchange. We can, for instance, use, if we wish, phi to the minus 1, which sends b to a. And so in the same way, phi to the minus 1 get f divides g. As f and g are both monic polynomials, if one divides the other and backwards, they must be equal. So, it follows f is equal to g. No, if g divides f and f divides g, they must be equal up to multiplying by a unit, but they are minimal polynomials, so the leading coefficient is 1, so they are equal. Okay, and so this proves it. So we will use this result immediately to prove something which will turn out to be half of what will be called the fundamental theorem of Galois theory. So in the moment, it doesn't really look so much like something, but we will see this is half of the proof of the, in some sense, main theorem of Galois theory. Is the following statement. So theorem. So we take a Galois extension. So we ask ourselves, we look at all the elements in the bigger field which are invariant under the whole Galois group. All phi in the Galois group. Okay, what could this be? I mean, obviously, it's kind of clear if there's any sensible, if there's any unique answer to this, the only possible answer could be that this is K itself. And that's indeed the case. So if an element in the bigger field is invariant under the whole Galois group for a Galois extension, then it must already lie in K. You see again, here this is obviously false. You have this extension which is not Galois. The Galois group just consists of one element, and certainly to be invariant under it means nothing. It's not that. But here, for a Galois extension, this is the case. We'll later see quite useful. As I said, it's more or less half the main theorem of Galois theory. So it has obviously two directions. One is trivial. So I didn't even write it. This is equal to K. This is trivial. Because obviously, every element in K is invariant under the Galois group, because the elements of the Galois group are precisely those automorphisms of L which are the identity on K. So that's by definition. So now let's look at the other direction. So we take an element, A, in the bigger field, which is invariant under the Galois group. All phi in the Galois group. L over K, and obviously we have to show A is an element in K. Okay, so now we have to just, what we will do is we look at its minimal polynomial, and then we will use what we have here to show that this minimal polynomial is just x minus a. So, namely that the only root of the minimal polynomial, the only root the minimal polynomial has is a. So let's try to see. So let f minimum polynomial of a over k. As our field extension is a Galois extension, in particular it's normal, we know that it splits into linear factors over L. F splits over L into linear factors. And it also has no multiple zeros because, but anyway, we don't need this now, maybe. Okay, so let's take another zero of this polynomial. Let in L be another zero. Another or any zero, possibly different zero. Of f in L. We have to want to show that b is equal to a. So by this statement here, if two polynomials have this, if two elements have the same minimal polynomial, there exists an element in the Galois group sending one to the other, we know there exists an element in the Galois group sending a to b. So by addition, Galois group. Okay. B. But we have said that this element should have the property that every element in a Galois group sends it to itself. So by our assumption, we have that A is equal to B. So all the roots of f are equal. And f also doesn't have multiple roots because it's a Galois extension, so several. It follows that f is just x minus a. And so and f is a minimum polynomial of a over k. So this is a polynomial with coefficients in k. So that means a is in k. Okay, so you see how one can use this. So now, okay, slower than I expected, but okay, so now I finally introduce the Galois group of the polynomial. That we are mostly interested in the case where we're looking at the splitting field of a polynomial, and then that's the Galois group of the splitting field over the ground field. In that case, we call it the Galois group of the polynomial. So definition. Let f in Kx be a non-constant polynomial. Let L be the splitting field of f over k. So the Galois group of f is, all right, the Galois group of f, which is the Galois group L over k. Now, as I said, the splitting field is well defined up to k isomorphism. So any two splitting fields are k isomorphic. And so that means the Galois group of f is well defined up to isomorphism. Because if the fields are isomorphic, their corresponding Galois group is, the automorphisms are also isomorphic as groups. And we can, after all, according to the story, we can see this as a subgroup of the zeros, or so a subgroup of the permutations of the zeros of f. We had seen that. Or maybe that's actually, no. That we will see now, that we can see this, so we can Galois group of f as a subgroup of the permutations of S of L, where with R of f in L. Okay, so this looks a bit similar to what we did there for simple algebraic extension, but it actually is different. Let me state. So this last thing is what we are now going to show. So this is the following proposition. So let f in Kx be a polynomial some degree n, you call R, as I said there, the set of zeros of f in the splitting field. So zeros of f of f over k. Then we have the following statement. First, and that's the main thing somehow, the Galois group of f is isomorphic a subgroup of the symmetric group on R, and the number of elements in the Gottsche group divides n factorial. Okay, where n is the degree of the polynomial. Second statement is something different, which I just put here because it fits. So if all roots of f are distinct, we have no multiple roots, then f is irreducible as a polynomial in Kx, if and only if the Gottsche group of f acts transitively on the roots. So Gottsche group of f acts transitively on R. I'm not actually sure whether we use this, but it's interesting to know that one can see so let's try to prove this. Well, in some sense, it's similar to before. We would show again that if we have an element in the Gottsche group, it sends the zeros of f to the zeros of f, and thus induces us a permutation of the roots of f, and that indeed this gives us a homomorphism from an injective homomorphism from the Gottsche group of f to the symmetric group on R. So let's do it. So the Gottsche group of f, the Gottsche group of L over K, where K is the splitting field. Okay. So again, we use the same trick we have already used twice today. If A is a 0 of f in L, then, and is an element in the Gottsche group of f, then f of phi of A, f of A 0, so phi of A is also 0. Also an element in R. So thus, the restriction to R again defines as a group homomorphism. So thus, restriction R defines group homomorphism. So restriction to R from the Gottsche group F, which is the Gottsche group of L over K, to S of R. No, because obviously this gives us a permutation of the roots, which sends phi to R. Again, it's a group homomorphism because we have composition as on both sides as group operation. So if restricted to R is the identity, then also the identity. Because we can say that L is equal to K R, by which I mean if I add all the zeros, so we know that if we have a field over which our polynomial splits, like L, which is already the splitting field will be the field, the subfield of it, which consists of all the zeros of this polynomial. The zeros are R, so we just have this. And so if phi is the identity of all elements in R, and it's also the identity on K, then it's an element, the identity on this. And so therefore on L. So therefore, so the kernel of this homomorphism consists just of the identity, so this homomorphism is injective. And so the Algebra group is isomorphic to a subgroup. The image of the map, so a subgroup of S of R. Okay, let me briefly also show, this was the first part, let me briefly also show the second. Yeah, this has obviously two directions. So first, we want to show that if F is irreducible, so we assume all the roots of F are distinct. If F is irreducible, then the Algebra group acts transitively on the roots. So F has only simple roots. As F is irreducible, let F be irreducible, and we take A and B of its roots. So then, as it's irreducible, that we can also assume that it's monic. We just divide by the leading coefficient. So F is the minimal polynomial of both A and B. And then we can, again, use the same trick as before. So we have the extension to simple algebraic extensions. So thus, there exists a K isomorphism. I want to call it psi from Ka to Kb with P of A is B. And now, again, we have that L is the splitting field of F over K, and Ka and Kb are both intermediate fields, so it's also the splitting field of F over Ka and over Kb. And so we can apply the extension of field isomorphisms for splitting fields. So L is also splitting field. Of F over Ka. Thus, there exists an extension psi, which is an element in the Gottsche group of L over K, so the Gottsche group of F, with psi, phi, large phi, restricted to Ka psi. So in particular, phi of A to B. So it says if I take any two roots, elements A and B and R, there is an element in the Gottsche group which sends A to B. So the action is transitive. And so now for the converse statement, so we have to see that if the action is of the Gottsche group of F is transitive on the roots, then and we assume still that all the roots of F are distinct, then F is irreducible. So assume that the Gottsche group, we do some kind of contraposition, the Gottsche group of F acts transitively but F is reducible. We have to show that the assumption we make here is wrong, then we have to show that not all the roots of F are distinct, that F has multiple roots. Okay, so let now G1, G2 be two irreducible factors of X. Of F. And we take, so let A1 be a root of G1 L. No, L is a splitting field of F, so it also splits G1 and G2, and B, say, A2, a root of G2. By the fact that the Gottsche group acts transitively, we know there's an element in the Gottsche group which sends A1 to A2. So as the Gottsche group of F acts transitively, R, now both A1 and A2 are elements of R because G1 and G2 are factors of F. There is an element in the Gottsche group. Of F with of A1 is equal to A2. And now we can once more apply the trick. Because if I take G1 of A1, apply phi to it, what's that? Again, this is a polynomial with G1 is an irreducible factor of F, over K, so it's a polynomial with coefficient K. So again, we can let phi go into the polynomial. A1 of A2. And obviously, 1 of A1 is equal to 0, so phi of it is also 0. So we see that also A2 is a 0 of G1. Also of G1. So A2 is a 0 both of G1 and G2. So it follows it's a multiple 0 of G1 times G2 and therefore of F. No, it means that G1 is divisible by x minus, so is divisible by x minus A2. G2 is also divisible by x minus A2. So G1, G2 is divisible by x minus A2 squared. And so also F is divisible by x minus A2 squared. OK. Maybe I will stop here. So I will almost finished with the description of these Galois groups. So we'll briefly do that, have some examples, and then we come to the fundamental theorem of Galois theory, which, as I said, will relate for a Galois extension the intermediate fields of the Galois extension to the subgroups of the Galois group. And that's used as a tool to study these field extensions. And then after that, we will use these results to study a classical problem, namely when can a polynomial in one variable be solved by radicals? So when can you find a 0 of a polynomial in terms of just taking square roots, nth roots, third roots, fourth roots, nth roots, and plus and some expression plus and minus and times in terms of this. This was a problem that had been studied for many centuries, and then it was solved by Galois, using, and for this purpose, he invented Galois theory. Okay, thank you very much. Are there comments or questions? Not, I wish you a nice evening and a good weekend. And see each other next week. And I will also send you this thing about the people who, postdocs or faculty who is associated to you this afternoon, this evening. Okay.
Thank you, Professor.
Mm-hmm.